4.2. We did all that work with sigmas and summations and shortcuts, and the video was kind of long, and I apologize for that, but we have to have a solid base in that in order to do what we're going to try to do today, which is deal with these things that we call Riemann sums and ultimately limit definition. The big stuff that we're working on here is we're trying to estimate area under a curve. And the way we're going to do this is, well, the setup of the problem, we're looking for the area. Here's two curves. They're supposed to be identical. We're looking for the area under the curve, under this f of x, same f of x on both graphs, in between x equals a and x equals b. So we're supposed to estimate that area. And we're going to do this doing what this thing says in the box. Approximate it with rectangles whose area is equal and whose endpoints are on f of x. So I'm going to kind of call on technology here a little bit. So I'm going to try to do this as best I can. This one over here on the left, I'm going to try to create rectangles. And these rectangles are going to have this width. And I'm going to do it so that the left endpoint of each of these rectangles that I create is going to hit f of x. Okay, so there's the first one. And there's the second one. And the third one. And the fourth one. And the fifth one. So there's 5 rectangles. Each rectangle hits the f of x on its left side. So it's left side. So each rectangle is supposed to have the exact same width, and each rectangle is going to hit on its exact left-hand side. Now on the other side, on this other picture, I'm going to do the same thing, but this time, instead of having the left side of my rectangle hit the f of x, I'm going to have the right side of my rectangle hit the f of x. So what's that going to look like? Whoops. I don't want that. I need this. I don't want red. Let's make it blue. Okay, so undo this. So this rectangle, we're going to have the right side of the rectangle hit the graph. And last but not least. Okay, so we've got red and we've got blue. Do either of them do a really good job estimating the area under a curve? No, neither one does an exceptionally good job. But the theory is supposed to be there are 5 rectangles in each picture, and they're both supposed to be exactly the same width. So if I wanted to estimate the area under the curve, this is what I would do. I would set up a sigma, a summation. If I want to find the area under the curve, I'd do sigma I equals 1, in this case to 5, but we're going to say 1 to n because I put 5 rectangles in because it made for a nice picture. But the truth is I might use a different number than 5. And if I wanted to find the area of this rectangle, I would do the length times the width. I'd find length and the width of each rectangle, and I'd add them together, and after summing all of that together, I'd have what I wanted. Well, how do I find that, the length and the width? Well, the width of each of these rectangles, let's think about this. Each of these rectangles, there's 5 of them. So couldn't I take, if I wanted to find, I'm going to call this width change in x. Change in x. That change in x is going to be the difference between b and a divided by, in this case, 5 rectangles. If I want to find how wide each rectangle is, I take the length of my interval, which in this case is b minus a, and I divide it by the number of rectangles. So in this case, it would be 5. So that would give me the width of each of my rectangles. And the same thing's going to hold true for the red ones, because this is also a change in x, and you would find it exactly the same way. But now what about the length of each rectangle, or in other words, how tall it is? Well, how tall it is going to be based on the height of each rectangle. So on this side, on the red side, if I wanted the height of a rectangle, maybe I should change this to the height times the width. That's probably a better word, the height times the width. The height of each rectangle is going to be f of the left endpoint. F of the left endpoint of the rectangle. What do I mean by that? So if you look at this first rectangle, we'll call this one number 1. So if I look at rectangle number 1, its height is f of a. Rectangle number 2, its height is f of, it looks like f of 1 or whatever that first x value is. Third rectangle, f of 2. Fourth rectangle, f of 3. Fifth rectangle, f of 4. And we'd come up with what each of those values are. Over on the blue side, the height is going to be f of the right endpoint. So if I did the same thing and I said, here's my first rectangle, the first rectangle's height would be f of 1. The second rectangle's height would be f of 2. The third rectangle's height would be f of 3. The fourth rectangle's height would be f of 4, and the last rectangle's height would be f of b, or in this case, f of 5. What do I mean by that again? The fourth rectangle's height is f of 4. Put 4 into the function and find out what its y value is. So what does all of this mean? If I wanted to come up with the area over here, the area under the curve on this side, I would do a sigma I equals 1 to n of my f of my left endpoint times change in x. If I wanted to do it on the other side, I'd do my area would be equal to sigma I equals 1 to n. This time, f of my right endpoint times change in x. Well, how do you know which one to use? Well, you're going to have some instructions. Okay, we are going to find that the f of the right endpoint is much easier to deal with. And if you want to find what the right endpoint of each of these rectangles is, if you liked it better when I went through the blue one because the first rectangle was f of 1 and the second rectangle, the first rectangle was f of 1 and the second rectangle was f of 2 and the third rectangle was f of 3 and the fourth, that was a lot easier to keep track of than the red one. Well, that's exactly what we're going to try to do. Because if I want to find the right endpoint, it's going to be a little bit easier to deal with because the right endpoint is always going to start with a. What's a? A is your left bound, the lower bound, plus I, or a plus a number of change in x's. A plus I times your change in x. So this is f of a plus I times change in x times change in x. Oh my gosh, Mr. Perkins, where did that just come from? Well, that I kind of just gave you. That thing in green is a shortcut for finding that right endpoint, and I think it's one of those things that you'll be happier with if I just give it to you than if you try to sort it out. So how do we know which one to use? If we don't know how many rectangles to use, if it's a generic number, always go with the right-hand one. Always. If they're giving you like 3 rectangles and you can sort it out, then use whichever one you want. Now, do either one of those areas do a very good job of sorting out what that number is supposed to be? No. The left one is what we call, the left one would be what we would call, this red one would be what we would call a lower sum. This would underestimate. This is called a lower sum. It underestimates. I can't spell, sorry. It underestimates. The blue one would be what we would call the upper sum. Why? Because it overestimates. How could we make them more accurate? There's your question down in the bottom. How do we make these approximations for the area under the curve more accurate? I hope that you could recognize if the rectangles weren't quite as wide, they'd both be off by a little bit less. Some people might say, what if you took those two and you kind of averaged them together? Well, that's actually not a bad idea either. What we're going to do is we're going to put in more rectangles. How do we make these approximations better? Put in more rectangles. What's the best? Put in an infinite number of rectangles. And that's where you're going to find this thing that we call the limit definition. What's the limit definition? If I want to find the area under a curve, area under a curve is going to be, we're going to use this blue definition that I have up here. We are going to take the right endpoints. We're going to use the right endpoints. We're going to do sigma for I equals 1 to, I don't know how many rectangles. The more we put in, the better. That's why there's an n on the top, not a 5 in my example I had before. Of f of my right endpoint times change in x. That's the limit definition. Well, that'll get us an area. Is it going to be accurate? It'll be better if we put in more rectangles. The way we make it most accurate is we take the limit as the number of rectangles becomes infinite. Limit definition for area under a curve. And that looks, oh my gosh, that looks like it's going to be tough. And I will tell you, it's going to frustrate you a little bit. Why? Because there's a lot of pieces. So I'm going to stop here with this one. This is your background information. Why do we need it? What's all this called? The big thing that we got to put together with all this, either one of these things are what we call a Riemann sum. Either one. Take a bunch of rectangles, put them all together. It's called the Riemann sum. And we'll put this in play in the next video.